Hello, everybody. My name is Dr. Langis Michaud from University of Montreal. My pleasure today to talk about optimizing oxygenation of the cornea when fitting 1-fit Met and 1-fit Met plus scleral lenses. Here are my disclosures. Scleral lenses are part of the armamentarium of eye care practitioners around the world since almost 80, 90 years. From blown glass lenses, the technology evolved to modern scleral lenses, mostly due of the work of Don Ezekiel and Perry Rosenthal from the United States. They took advantage of the newly gas-perm material introduced in the market in the 1980s to regenerate, in fact, interest and to remanufacture scleral lenses in more oxygen deliverable material. And so it became, with the years, and nowadays it is, standard of care to treat ocular surface disease and or to restore vision on compromised or irregular corneas. But as with any other devices, scleral lenses have some limitations. And before fitting scleral lenses, we have to ask ourselves, is there enough benefit versus the risk that we have to fit this eye with scleral lenses? And 99% of the time, it will be the case, and we will just proceed with the fit. But one of the limitations of scleral lenses may be, in some cases, oxygen delivery to the cornea, especially on those patients with compromised endothelial function. And we have to remember that the oxygen permeability of the material, despite the fact that the lenses are made with very high decay material, is related to the thickness of the scleral lenses. Scleral lenses are thick, so even if the material is highly permeable, the thickness of the material itself preclude oxygen to deliver freely to the cornea, as it is with regular gas-perm lenses or soft lenses, which are way thinner compared to scleral lenses. The weakest link of the equation here is certainly the tear reservoir, the fluid reservoir, because fluid are not so permeable to oxygen, and the decay of any fluid, according to Dr. Benjamin, is around 80. So, and you have again to divide that number by the thickness of the tear fluid reservoir, which may become, significant with some cases or with some fittings. The material of the lens itself obviously will dictate that, and we have also to understand that once the lens is settled on the surface of the conjunctiva in the eye, it's a kind of a seal-off environment, meaning that there's no real tear exchange. So there's no real oxygen that can be provided by the tears as it is with other contact lenses. And there's no tear mixing as well. Dr. Lin from Berkeley proved that. So there's not really a kind of, turnover of in the reservoir that would somehow, replenish, the fluid reservoir and oxygen. So that's not existing really, or it's very, very minimal contribution to the equation. So at the end, we have a system that can really penalize cornea and the ocular environment under that lens from oxygen delivery. And so we published a model in 2012, a theoretical model. Obviously, it's not a practical model. It's not a study. It's a theoretical approach. And that paper was cited over 100 times over the years, almost 10 years now. And we suggested that to alleviate hypoxic stress to the cornea, scleral lenses must be fitted with a tear fluid reservoir of 200 microns at the most, and the lens thickness must not go over 250 microns. It may be difficult to comply with those requirements if you have a very high convex lens. For example, a +20 or +10 lens will be thicker than that, just by the nature of the power of the lens. So anytime you increase the thickness of the lens, you have to compensate at the given point with either the oxygen material, oxygen permeability material, and or the tear fluid reservoir thickness. And that model was confirmed by Compian and Wiseman in 2013, 2014. And at that time, they estimate with their mathematical model, again, that the decay of the lens material must be at least 150 to respect these criteria. So that was the case, and that was the science in 2013. It took 5 years for Dr. Kim from Berkeley to model and other mathematical model. And at that time, this model helped us understand, at least based on the study, that the permeability of the material, the dk over t, so the permeability of the material divided by the thickness of the lens, is the key factor driving oxygen delivery to the cornea. And the tear fluid reservoir, the thickness was not so in play in that particular model. But it was proven by Vincent, by the Kim's model, slightly underestimate the edema triggered in this system, and was really not applicable if the tear fluid reservoir went over 800 microns, which I don't recommend, but in some cases it may be the case. Kim came out with some other work with Dr. Radke from Berkeley again in 2020, and their contribution at this time was to look at the oxygen delivery from the limbus vasculature, and the exchange of gas, bicarbonate, and the carbon dioxide over there may play a role. And so they predict that hypoxia occurred regardless of the permeability of the material, but it was located centrally. So the peripheral retina was, the peripheral cornea was not affected by the edema or hypoxic stress, mostly because of the contribution of the vessels around the limbus, which was a good finding. And they estimated that in any case, the edema in the central cornea never reached over 4%. And they compared it to physiological edema, and we'll see that it's not really a very good comparison. And more recently, the same team, Kim and Radke, came up with some other mathematical model, and they estimated that it's possible to minimize swelling to less than 1% centrally in the central cornea if we manufacture lenses with some scleral and with some embedment that will allow direct transmission of oxygen through the lens and not by diffusion through the material. And if we fit the lens with the minimum tear fluid reservoir and using a highest DK material. So in fact, it confirmed the approach that we published 10 years ago, meaning that you have to limit the vault over the cornea, not touching the cornea, obviously, not touching the limbus, but you have to limit that vault, and you have to use the highest DK possible in order to prevent any kind of hypoxic stress occurring on the cornea. And it's a confirmation, a solid confirmation of what we propose. So if you look at what happens when you do a clinical study now, it's not theoretical model. These were theoretical models. Now look at the in vivo study. We published that a few years later in 2018-19. And what we did is we evaluate at the corneal level with electrodes the oxygen consumption before and after sterile lens wear. And what we were able to establish is that if you increase the vault by 200 microns, coming from 200 microns at the beginning, which is the idle and optimal vault over the cornea when the lens is stabilized, and we increase it to 400 microns, we reduce by 30%, which is significant, the oxygen delivery to the cornea, and or the consumption of oxygen after lens removal was increased by 30%. That's another way to explain these results. And so it was significant. So there's an impact at the corneal level if you just go from 200 to 400 microns. So every time you go with increase thickness up to 800 microns, as it was proven in the theoretical model, then you penalize oxygenation to the cornea. Again, more recently, Fisher and Vincent look at the closed eye environment, because the other studies were, and the theoretical model concerned the eye that when they are open. But Fisher and Vincent looked at the closed eye environment, extended wear mostly. And what they found is that in that particular case, the tear fluid reservoir is the key factor. It's not surprising because there's no direct oxygen delivery to the ocular surface because the eyes are closed. Oxygen cannot reach that. So the decay of the material has nothing to do because there's no oxygen to transmit. And so period. So the tear fluid reservoir is the key factor under closed eye condition. They again proved that the edema is stromal in nature, which was also proven by Vincent in the open eye model. And they also confirmed that it occurs very rapidly in the matter of the first 45 or 50 minutes after lens application on the eye. Then you generate enough hypoxic stress, and after that it remains stable like a plateau for all wearing hours. So it never goes away, it never fades out. The edema, the hypoxic stress, remains for the entire wearing period of time. Nifedov, a student at Pacific University, looked also in his thesis published in 2016 at the overnight wear, and he proved that the swelling of the cornea is proportional to the vault over the cornea. So again, here, the thicker the vault, the thicker the reservoir is, more, less oxygen will be delivered to the cornea and more swelling it will generate. So again, it's a confirmation of the previous model, and we begin to understand that under open eye or closed eye environment, as long as you increase the vault over the cornea, you penalize oxygen delivery. So sterile lenses induce edema, period. Regardless of the lens, regardless of the fit, regardless of what you're doing, you will generate an hypoxic stress that will be translated in corneal edema. Habitually, it's less than 4%. I agree. Any clinical study made on wearers, robust normal cornea will show you that you accumulate less than 4%. In fact, in average, it's between 2 and 3%. And most of the authors will compare that to physiological edema. Nothing happens with physiological edema. It's 4% when you wake up in the morning, and then the cornea restore, and there's no consequences on the long term. But physiological edema does not last. It does not last more than 1 hour after awakening when the eyes are open, contrary to the fact that, edema, as we saw in the theoretical model and the practical, studies, is lasting for all the hours that the lenses are worn. So it's not the same hypoxic stress. The stress is constant and chronic when you are wearing sterile lenses compared to physiological edema that is non-constant, every day for sure, but it fade away, and the cornea can restore itself in a matter of a few minutes after awakening. And certainly it proved also that under closed eye condition, it's over 4% and may reach 20% in some corneas, and it's really proportional to the tear film, the fluid reservoir thickness. So again, daily wear, decay over time, the material plays a role more importantly than the reservoir, and under closed eye condition is the contrary. The tear reservoir plays a significant role compared to the material. And it's possible to alleviate hypoxic stress if you ramp up the decay of the material, if you reduce at the lowest possible the vault over the cornea, and if you design a lens with embedment, which is not really possible actually, it's on research only, but if you fit the lens accordingly, then with minimal vault and eye decay, at least you minimize the hypoxic stress over time. And why it is important? Because clinically speaking, it may generate inflammation. That study proved that you can generate accumulation of leukocyte in the reservoir, which is pro-inflammatory, and you can generate reaction of the immune system if you penalize that cornea of enough oxygen. And in their conclusion, they said that for every 50 microns increase over 200 microns, you increase by 2.24 times the odds of presenting tear film fogging and midday fogging and the accumulation of leukocyte pro-inflammatory cell in the reservoir. So this is significant because, again, it's a proven fact that if you generate hypoxic stress chronically, you may generate immune reaction over time. And again, we see that it's occurring, this edema is occurring very fast, between 60 and 90 minutes after lens insertion, application, and it remains constant throughout the wearing period. Again, study by Kim and Dr. Lin in Berkeley proved that in any case, you will generate hypoxia. So the curve never reached zero under any circumstances. And the decay over T of the entire system must be over 40 in order to minimize at least the hypoxic stress, which means that the highest decay material possible that we have on market today, 200, and the volt of 200 and or less, a little bit less, once the lens is stabilized. And the time course, again, it's all over the place during all wearing hours, and it's stromal in nature. It's not the epithelium that is swelling, it's the stroma that is swelling. Obviously, that's relative to the nature of the cornea. You know, the swelling occurs in the stroma because this is where water can accumulate, not in the epithelium. So again, this study by Vincent proved this. So the clinical impact is that mostly we don't see a lot of big problems over time when the cornea is robust, normal, young, healthy patients where the studies on which studies were made most of the time. But we don't know the long-term effect on those normal corneas. Let's say that you fit a patient at 30 years old, 35 years old, you know, when he'll have a cataract surgery at 60, 65, what will be the impact of wearing scleral lenses inducing hypoxic stress during 30 years? We don't really know because we're not there still. We'll see when that will occur. But to remain on the safe side, we have to minimize this hypoxic stress as much as we can. And as for extended wear, I think that the studies are quite clear. It's you have to ask yourself the big question about the risk and benefit, because the risk is very high here, because you can generate up to 20% of edema with blurred vision, with corneal decompensation, perhaps a higher risk of infection. So you may have to prescribe this for recurrent erosion, for example, or when any other things fail to treat that patient. But again, it's a risk benefit, and you have to manage this patient very, very closely, but never recommend on a regular patient to wear several lenses under extended wear mode, certainly not. And we know that edema is present. This photo here shows corneal edema through a scleral lens while it's worn. So it may be visible at 4%, not really, but it becomes visible at 7, 8, 9%. So if you see that cornea here, you know that your 8, 10% corneal swelling, and probably there's something going wrong. Either your decay of the material, your vault is not okay, or the cornea itself, the endothelial function, is compromised at a given point. You may generate blebs. Also, we'll see some photos on that. My colleague, Dr. Giasson, proved that with a team of researchers here in Montreal. We can promote limbal injection. We can have a modification of the corneal curvature, which may be translated with a myopic creep. We may generate neovascularization, and we may affect the endothelial cells on the long term as well. Here are the photos coming from Dr. Giasson's article. These are the bloods generated, very few minutes after lens application. When still there are some tear exchange, the lens was not really stabilized in the first 20 minutes, but it tells you that up front, the cornea reacts and the carbon dioxide accumulates in the system, which is a clear sign of hypoxic stress. And when the first study, Santos, published about the blebs in the 1970s, it brought the entire industry of soft lenses to find new materials, and the silicone hydrogel lenses were launched in response to the bleb and many other alterations that hypoxic stress occur at that time. So this is why we are moving toward new materials with higher decay, and we have better understanding of the relationship between several lenses and the cornea on the long term. In average, if you look at several lenses produced in the market, they are thick for the 450 microns. Manufacturers recommend to have a higher vault, 300 microns, 400 microns. And they recommend materials with DK of around 100. If you compute those numbers, you will end up with a DK over T of 12, which is certainly not sufficient to alleviate hypoxic stress. To the contrary, it just promotes corneal edema. So if you want to alleviate that hypoxic stress, the philosophy is quite clear. You have to have a thin lens, a thin tear film, a minimal vault, and you have to have the highest DK possible. You have to monitor your patient closely, especially if you have endothelial dysfunction or a very low endo cell count, less than 1,000 cells per millimeter square, may be a contraindication to fit sterile lenses if you have not other option available for that patient. And at that time, you have to monitor the patient very, very carefully, but still to select the highest decay material, the thinnest length possible, and the minimal vault. This is with these principles in mind that the family of the one-fit lenses were designed and introduced in the market, from the one-fit 2.0 a few years ago, one-fit Asian for the smaller corneas and the particular profile of the Asian eyes, to the new ones, the one-fit Med and the one-fit Med Plus, that are more indicated for corneas that are needing support, meaning ocular surface disease, keratoconus, irregular corneas, or when they are medically indicated to treat dry eye, for example, where the larger the lens is, the better it is. But habitually, my go-to lens nowadays, it's the one-fit Med with 15.6 in that family, because, it's fully customizable. And certainly I'm very, very comfortable with all the feature of that lens. And I'm comfortable that with the philosophy of having a thin lens fitted with limited vault and high oxygen material, I will protect the cornea of my patient on the long term. So you have 4 different areas in that lens that can be modified independently. The central, obviously, vault may be modified, plus or minus, depending on how much you want to vault and how much the cornea needs to be vaulted. The mid-periphery can be adjusted as well to limit. Habitually, my go-to vault over that area is 150 microns, 175 microns, when the lens is stabilized again. And with that, I have very, very good product. But if I just increase the sag of my lens, the central vault, obviously my mid periphery will increase at the same time. But with the computer tool that Blanchard provide me with, I can modify it and see what happens to my tear profile, and I can estimate and compute the exact number that I have to lower this mid peripheral area to keep my vault at 150, 175. And that mid periphery, if you change the vault of that section, you will modify the power of the lens, because the fluid in the reservoir, the reservoir itself, tear fluid layer, is thick enough to generate power. And if you modify the shape of that reservoir layer or fluid layer, you will modify the power associated with it. So you need a computer to evaluate that. And it happens in every other lenses in the market, and the manufacturer will not tell you that. But if you call your lab, your consultant, say, okay, I want to have this modification and to lower my mid-peripheral area by 100 microns, they will give it to you, but they will not tell you that it will change the power, the final power of that lens, because it influences the final outcome. And you may modify the limbus. Go to vault over the limbus is 75 to 100 micron habitually, and the edge can be modified by quadrant or symmetrical or asymmetrical, depending on what you want, just to match the profile of the conjunctiva. We know the conjunctiva can be highly irregular, can be highly toric, and not certainly in perpendicular meridian. So it's all over the place. So you have to adapt by quadrant the landing of your lens to alleviate compression or lift out. So you can modify these details independently with the one-fit lens. All zones are really independent. One-fit Med is for more normal corneas, smaller corneas, when you have the need to cover a little bit more than with the one-fit 2.0 with the regular one-fit. One-fit Med Plus is certainly for, ocular surface disease eyes, the dry eye patient, where you need, a 17, 18 millimeter lens. And again, obviously the vault will be higher. You may use it for the pellucid marginal degeneration as well, because if the pellucid ectasia is very low on the cornea and you want to vault nicely over that ectasia, you cannot land shortly on the conjunctiva, so you have to have a space over there. So you have to use larger lenses, and both of them can be effective, but one fit med plus may be a better alternative depending on the profile of the cornea, certainly. So the central zone can be prolate or oblate. Oblate means, let's say that you have a post-LASIK patient, the cornea is oblate, so you have this scleral lens, but if you have a regular profile, a prolate, you'll have a thicker portion of the fluid when you are lying in the mid periphery. So you have to bring down that central vault without changing anything else, because you're well aligned in the mid periphery and over the limbus. So oblate design will help you to do that. I'm also using the oblate geometries to optimize the power, because what you're doing when you are prescribing oblate geometries is you just flatten the base curve, and flattening the base curve give you minus power. Let's say that you compute your lens and you have a final lens of minus 10 power. You may be happy with that, or you can do better with the same lens, the same sterile lens. If you go with an oblate design, you will reduce the power. But if you go with oblate, you have to over vault at the beginning, and then after that prescribe the oblate to have a very good clearance over the cornea. But the final result is that you will optimize the power. A little bit complicated, but talk to the consultant of Blanchard and they will drive you through that option, and it's certainly to the benefit of your patient. Let's say that you have a multifocal patient to fit with this lens, and you have a -8 plus 250 add. Then if you use an oblate design and you end up with a -2 lens instead of -8, still compensating for a -8i, but because of the powers and the curves of the lens and the tear reservoir power, then you have perfect vision at distance. A -2 plus 250 add, it's way better to prescribe in a presbyopic patient compared to -8 add plus 250. Immediately coming from -8 to -2, you have an increase in the image size. So you help your presbyopic patient. That's one way to improve the results with presbyopic or multifocal lenses. Mid-peripheral and limbal zone also can be modified by plus or minus 300 microns, and maybe adjusted specifically by quadrants and by 25 micron steps. So it's highly customizable to the profile of the cornea, the profile of the conjunctiva, depending on what you want to achieve with your fit. Same thing for the landing zone alignment. You can modify it just to land nicely on the conjunctiva without doing any kind of compression or lift off, which would be felt as uncomfortable by the patient. Here are the values I mentioned previously. So at application, we want to have around 250, 300 just at application, 1-to-1 ratio with the lens thickness. After 30 minutes, it will drop down to 220, 225 microns. And after 4 hours, when the lens is fully stabilized, you'll end up with 150, 175 microns. So I really like to see my patients at the end of the when I do my follow-up, so I can evaluate what is my final vault over that cornea and over that surface. Some conjunctiva are smoother than other ones, and the lens will sink more. So you may be surprised. You have this perfect fitting after 30 minutes, around 200, 225, and a week later at the end of the afternoon, you see that the lens has just collapsed on the eye because you lost more fluid compared to the average, and then you have to revisit your fit at that time. The mid-peripheral zone, as I mentioned, around 150, 175 microns, will drop down to 100, 125 when the lens is stabilized. Same thing for the limbus. We started with around 100 microns, and then we end up between 50 and 75, just to vault enough and not too much, because if you vault too much over the limbus, this is where you open the door for debris to entering in the reservoir and to pollute it. So mid-defogging, part of it is because the limbus vault is certainly too high compared to what it's supposed to be, and you increase the suction effect and the debris that goes in. There's no tear exchange, as I mentioned, so there's no they cannot be flushed away, and so the debris accumulate, and then you end up with the midday fog. And one of the way to fix that issue is to lower the vault over the limbus and to keep it, between these values, 50, 75 microns when the lens is stabilized. Many more extras. You can visit the website for more details. You can notch to accommodate for pinguiculas and for pterygians. You can have extralimbal clearance if you need it. You can have multifocal, distance center, or near center, depending on what you want to achieve, or front toric if you have residual astigmatism. So in conclusion, that lens as it is, and you can apply it in any other lens you may prescribe, which would be your preferred lens. You have to alleviate hypoxic stress on a chronic basis to that cornea. And the way to do it, high decay material, 200. It's now available. We have several materials available for several lenses at that level, 180 or 200 DK material. Limit the lens thickness. The 1/5 is on purpose made thin, but ask your lab. They can do whatever you want. If they produce lenses very thick, 400 microns for -3 lens, send them back and say, no, it's too thick for me. 250, 300 microns at the most, please. And they can do that. They can't afford it. The lens won't break. The lens won't flex if it's well designed. If it's not well designed, obviously they'll have issues. But some lenses you have to be thick in order to have the geometrical stability of the lens. So these are not products I'm working with because they are too thick and it penalize too much the oxygen delivery to the cornea. IDK, lens thickness, minimal. The vault over the central cornea being minimal as well, around 200 at the beginning and 150 at the end of the day. Lower, vault over the mid-periphery and the limbus. We saw that, the edema, based on the theoretical and practical studies, is located centrally. So this is where, because the vault over there is higher, so we have to minimize it. And with this, you'll be successful and you'll preserve the ocular health of your patients. And always, as I said, evaluate the risk and benefit before fitting sterols. That's the gold standard and the rule to observe. So I thank you very much. You can email me your questions if you have one, langis.michaud, langis.michaud @umontreal.ca. So with that, it was a pleasure to meet with you. Sorry for not being there in prisons, but next time when the COVID will be gone, we can meet in a meeting and have fun together. So take care.